So today we're looking at carboxylic acid and esters, and over the next couple of lessons you'll look at esterification, and we will also be conducting a practical making our own esters as well. First, you need to recall what a carboxylic acid actually is. Remembering it contains a carboxyl group. The carboxyl group is both of these groups together. So you've got a hydroxy here in red and a carbonyl group here in maroon. These are just some images of 3D carboxylic acid molecules. Just remembering that the carboxyl group is on the end of the molecule and it is automatically assigned the number 1 for that carbon, for this carbon here. So we don't need to assign any numbers when we're naming our carboxylic acids. You may know of these common names of carboxylic acids, acetic acid being the most common one. However, when we go to name them in the HSC, you're best off just using this method, which is the naming convention that we've learned. So there's a couple of ways that you can make a carboxylic acid, and that is the oxidation of either a primary alcohol or an aldehyde. So just recalling that a primary alcohol such as ethanol will oxidize in its first step to form an aldehyde, which is this here, and then that aldehyde will further oxidize to form the carboxylic acid. Just having a look at a few properties of carboxylic acids, and it's important to recognize that they've got two highly polar groups. Okay, so the carboxylic acid, the carboxyl group itself contains two polar groups. One being the very polar hydrogen bonding hydroxide group, and also the carbonyl group is also a polar group with its positive and negative end, obviously not being able to hydrogen bond, but still polar. Because of this, carboxylic acids have a high boiling point. Recalling that the carboxylic acid, which is this molecule down here, this is ethanoic acid, and it is able to form a dimer with another ethanoic acid. So this is the bond that is present between the hydrogen of one hydroxide to the oxygen of another carbonyl group, and the same occurring at the top, that these molecules come together to form a dimer, which essentially doubles its molecular mass, making it have greater dispersion forces. So the boiling point of a carboxylic acid is much higher than its corresponding alcohol, ketone, and aldehyde of the same mass. So here we just have three organic molecules, a aldehyde, alcohol, and a carboxylic acid. They all have a similar molar mass, and we're just making a comparison of their boiling points. So here we have a 3-chain aldehyde. Its mass is slightly smaller because it doesn't have an extra hydrogen. However, it still has a pretty high boiling point of 49 degrees because it is able to form dipole-dipole interactions with other propanol molecules. However, it's still not as high as its corresponding alcohol. The alcohol's molar mass is a little bit greater because it does have a couple of extra hydrogens, and it is actually able to hydrogen bond with other propanol molecules. So we can look at its boiling point and say that it's almost double that of its corresponding aldehyde. And down here, we've got a carboxylic acid. It does have a similar molar mass to the other two molecules, but just having a quick look at it, it only has 2 carbons, not 3. And we can see that its boiling point is actually considerably higher than the other two, despite having 1 less carbon. So its molar mass is very similar because it has 2 oxygens rather than 1. But its boiling point is higher because it is able to form dimers with another. So this is ethanoic acid. A dimer would be formed between 2 ethanoic acids. And that's why its boiling point is quite high in comparison to the 3-chain alcohol and 3-chain aldehyde. So looking at solubility in water, carboxylic acids are soluble in water, and it follows the same trend as the other molecules, is that as that carbon chain gets longer, so as this chain here becomes longer, there is going to be a greater portion of the molecule that is non-polar, and so it would not be able to interact with all the water molecules. So solubility in water will start to decrease. When carboxylic acid molecules, they're forming a dimer together. When they actually are mixed with water, the dimers actually break apart and the carboxylic acid will interact with the water molecules. So we can just quickly see here that the first 4 carboxylic acids are very soluble, and then as that carbon chain gets longer, we can see that the boiling point is obviously still increasing, but the solubility will start to decrease. So we kind of already spoken about carboxylic acids being weak acids when we've looked at acetic acid. And we know this is acetic acid right here. We know that it will form an equilibrium system with water to form acetate ions and hydronium. We know that this reaction lies to the left-hand side, so in terms of how much hydronium is being produced, it would not be as much as how many molecules of acetic acid that there actually are. So in terms of looking at carboxylic acids, we do say that they have small K values. Just by looking here, we've got 10 to the negative 4 increasing to 10 to the negative 5. We do say that's small, and we do call them weak acids because they're not 100% dissociating. But we can also think that the acid ionization constant for these acids aren't as low as a lot of the other ones that we've seen as well. But we still say it's small because it's not ionizing completely. So a carboxylic acid can be neutralized and it will form a neutral salt and water. So the example here is acetic acid plus sodium hydroxide to form sodium acetate plus water. Now we're going to have a quick look at esters. So esters actually form fragrances, and we've got an image here of fruity fragrances because that's what we make when we do esterification. So esterification is the reaction between a carboxylic acid and an alcohol. We can classify an esterification reaction as a condensation reaction because it produces a small molecule such as water. In this case, the esterification reaction does produce water. So what happens is that the carboxylic acid and an alcohol come together, they form an ester, and they also form a water. So you can look at this as an esterification reaction, but if you're sitting an exam and you can't recognize it as an esterification reaction, you should be able to recognize that a water is being produced and is one of the products. So you can call it a condensation reaction as well. So what happens is the alcohol, which has a hydroxy group, the hydrogen from the alcohol will then come off that alcohol, and the OH from the carboxyl group will also come off the carboxylic acid, and the hydrogen and the OH come together to form the water. And so then that leaves open the rest of the carboxylic acid and the rest of the alcohol to come together and form a molecule, which is the ester itself. Doesn't make too much sense, but when we look at an image, it will make more sense. So in order for this reaction to occur, we need it to be slightly heated. And because we are heating volatile liquids such as an alcohol and a carboxylic acid, we do have to heat it under something called reflux, which we'll learn more about. And it needs the presence of a concentrated acid such as sulfuric acid as well. So this is what an esterification reaction looks like, or the production of an ester. You've got your carboxylic acid and you have your alcohol. And so what's being highlighted here we can see that this part of the alcohol forms this blue part of the ester. This red part of the carboxylic acid comes and joins the alcohol to form this part of the ester. And the two black parts of either the alcohol and the carboxylic acid is what's actually producing the water. Okay, so the hydrogen from the alcohol and the OH from the carboxylic acid. All right, so we've got these two molecules coming across, the hydrogen and the hydroxide coming across to form the water. And so then when the ester comes together, when we're drawing it up, it is an oxygen from the alcohol. It's got the rest of the carbon chain attached, but the oxygen used to have a hydrogen attached. So it has space to join up to this carbon here, to the carbonyl group from the carboxylic acid. We'll go through naming in a second, so don't worry too much about writing this down. You might want to draw some images, but I wouldn't worry about this stuff down here at the bottom. So the ester group is this carbonyl group, and the carbon from the carbonyl group is attached to an oxygen. So we call this an ester group. The name from the ester comes from the alcohol and also comes from the carboxylic acid. So if we have butanol plus ethanoic acid, this is the molecule that we actually get. So this is butanol, and then the hydrogen from this molecule has come off. And here we've got ethanoic acid, carbon, carbon here, and the hydroxide has also come off. So this is where they've come together. When we go to name this ester, the part of the alcohol gets named as a substituent. So here we've got 1, 2, 3, 4, so we will call it butyl. And the name of the acid, which is ethanoic acid, turns into ethanoate. So then we end up forming butyl ethanoate. We'll go through it a little bit more so you get more practice, but you just got to remember the substituent, butyl, comes from the alcohol, and oat is what's replacing oic acid. So if we're replacing oic acid from the carboxylic acid, ethane stays there and it gets replaced to ethanoate. So here's an example where we've got propanoic acid and methanol. So they come together, and we've got our old methanol, and here we've got our propanoic acid. And when we go to name that, the alcohol gets turned into substituent group. So we've got methyl, and this 3-chain carbon from the carboxylic acid becomes the ending name. So we've got propan, and we've changed the ending of the name to oat. So methyl propanoate. You can see that we've got acid as a catalyst, and we are still producing water. So if you're doing a balanced equation, you would have to, or a structural equation, you would have to include that water molecule as well. All right, so just a little bit more revision in terms of naming an ester, and I think this comes with practice. So if you could pause the video and just write this down, perhaps drawing or highlighting what part of the name goes where, makes it easier to remember later when you're studying for your trials or your HSC. So now we'll just look at some properties. So in terms of looking at an ester, I'm going to be looking at its reactivity to be able to reform back into its alcohol component and its carboxylic acid component. And in order for this to happen, another acid catalyst is also required, and we call this acid hydrolysis. So we've got the ester here, plus water, plus our catalyst to form our carboxylic acid and our alcohol. Base hydrolysis is one that we will actually look at possibly next week or so. And it also goes by the name of saponification. So you have an ester, which is then reacted with a strong base such as sodium hydroxide, and it will form the salt of a carboxylic acid and also an alcohol. All right, so we will actually go through this in more depth and properties of soaps later on. But it's important to know that this is a reaction of an ester. It's a property of an ester being reactive to be able to undergo this sort of change. So we've got an ester reacting with a strong base to produce the salt of a carboxylic acid and an alcohol. So essentially what we will be looking at when we look at soaps, we wouldn't be looking at such short esters such as this one. We'll be looking at a longer one such as this here, and they're called fatty acids. And when they react to form, when they react with a strong base, they form the salt of that carboxylic acid. And that carboxylic acid, the salt that is produced is what actually the soap will be. And so we can see that this salt here, it's got a very long chain, and that is its polar tail. The polar tail will actually be attracted to grease molecules that it's trying to wash off. And the polar head of the salt of the carboxylic acid is what will be attracted to the water when you're trying to wash, grease or oil off clothes or off anything like such as this image on the car. We will actually go through this in a lot more depth. So if you don't feel like writing any of this down, then that's okay, because we will be doing this later anyway.